Okay, in the first part, we talked about the forces, magnetic forces, QV cross B, IL cross B, creating a magnetic force. Now we're going to talk about the fields that are caused by currents. So it kind of works both ways. Currents are acted on by magnetic fields, but currents also create magnetic fields. So currents can cause magnetic fields. When we have a current, in this case, going up, there is a B field around it. And I'm not going to draw all the concentric circles, but they get weaker and weaker as you go farther away. So a strong B field right next to the current, weaker and weaker as we go farther away. And the equation that we use for this is mu 0 I over 2 pi r. It's really not too bad, and we're going to show this later, how this comes about. Mu 0 is a constant called vacuum permeability, which is 4 pi times 10 to the negative 7th. Newtons per meter squared, or Tesla meters per ampere. Okay, so let me show you how we use this. The currents cause magnetic fields, so the direction, though, is given by a new right-hand rule. And the new right-hand rule is actually, I think, a little easier than the old right-hand rule. What we do is we put our thumb in the direction of the current. So if that pen is the direction of the current, our thumb is in there, and our fingers will naturally curl around in the direction of B. It's really important to know how to do that. So in other words, the equation gives the magnitude, and then we're going to use our right-hand rule to get the direction. So let's start right here on this situation. I is out of the board. That dot means out of the board. So I stick my thumb so it's pointing back at me. My fingers will naturally curl around counterclockwise, and that's the direction of the B field. Similarly, if I put my thumb into the board, my fingers will curl clockwise. I hope I got that first one right. And then here, if I put my fingers my thumb in the direction of the current here, my fingers would go into the board on the right side and out of the board on the left side, and vice versa. So make sure you're using that correctly before we move on. Now, we want to find the B field at a point 2 meters away from this current carrying wire. The current's 3 amps. The distance from that is 2 meters. And we know we have the equation. We just plug that in, 4 pi times 10 to the negative 7th times 3 divided by 2 pi times 2, and we get 3 times 10 to the negative 7th Teslas at that point, only at that point. Closer, we'd have a smaller r, we'd have a bigger B field. Farther away, we'd have a weaker B field. The direction is going to be out of the board using our right-hand rule. Put the thumb in the direction of the current, wrap your fingers around, the fingers will be coming out of the board at that point. Now, let's take it one step further. So we found the value and we found the direction. Now, what's the magnetic force on a proton in this situation? Looks pretty similar. We've got a different current, a different distance, and we have a proton moving through. We're going to find out what the B field is, but if we have a proton moving through a B field, we know that that we can find the force on that. So the first thing is, let's look. Right-hand rule means the B field is coming out of the board that this proton's moving through, okay? And so then we have the QV cross B. We have to find the B first. Here's the B. Mu 0 I over 2 pi r is 1 times 10 to the negative 4th Teslas at that location. Again, where that proton is moving. Not closer, not farther, but right there at that specific radius. Okay, then we can use force is QV cross B. And I should go a little slower on this. The V is to the right. The B is out of the board. So when we use our right-hand rule, our different right-hand rule for forces, the way I do it is I put my fingers in the direction of the first one, rotate my fingers in the direction of the second one, and my thumb points in the direction of the third one. So we can get the force pretty easily just using the magnitudes. They're right angles, so the cross product goes away. And then what I find, is the force will be down. Now we've got 2 current carrying wires, and this is kind of a neat situation because if we look at this, each one of these current carrying wires creates a B field, and each one of these current carrying wires, we have the IL cross B, gets a force from the other B field. So let's look first at the force on I1. Okay, we know that the B field is going to be mu 0 I over 2 pi r in each one of these. Let's look at the B field created by I2. We put our thumb in that direction, we rotate our fingers around. At the location where I1 is, the B field created by I2 is out of the board. Okay? Below I2, it would be into the board. Above, it's out of the board. So now we've got a B field and we've got a current going through that B field, IL cross B. And so for I1, that force is going to be down using the right-hand rule. And if we really evaluate that, IL times B, which is just mu 0 times the current I2, right, because that's what's creating the B field, over 2 pi r. So if we put those I's together, you get mu 0 L I1 I2 over 2 pi r. Why did I group it like that? Because Newton's third law says it's going to be the exact same force of I1 on I2. If you want to do that, you could do right-hand rule. When we do that, from I1, the B field is into the board where I2 is. And then we do I cross B, and you'll find that the force on that one is up. So, same thing happens. The exact same expression. I1 and I2, commutative property of multiplication. So it's still going to be that same thing we found for I1. It's going to be looking a little different. We'd have I2L mu 0 I1 over 2 pi r. And the forces would be opposite because of the right-hand rule and Newton's third law. Let's look at solenoids. Solenoids come up a fair amount. Solenoid is just a coiled wire. And we put a current through that, has a length L. And I tried to show that in this case, that current in this 3D model, the current would be going over and into the board on the top. And if we keep following that current, it would be coming out of the board on the bottom, which is kind of important. So into the board on the top in this case, and out of the board on the bottom. And the reason that's important because each of those is going to be creating a B field. If we just look at the cross section, those two parts of wire right there, the parts that are going in and the parts that are going out, not worrying about the stuff that's coming around the front or going down the back. And what you see is the ones that are going into the board are creating this clockwise B field. The ones that are coming out create a counterclockwise. Well, you look in the middle, those things are going to add together to make a strong B field. That's why a solenoid is used, to create a strong magnetic field. And outside, let me just blow up one of those ones on the bottom. If I look at the B field from one of those loops on the bottom, you can see when it's above the solenoid, it would be canceled out by the B fields from the top parts of the loop. In other words, outside the solenoid, the B fields cancel. There's no net B field. And inside the solenoid, they add together to make a strong B field. And so we can actually, we can derive this elsewhere, but we have some terminology. We call the total number of turns capital N, the length L. Then we use this quite a bit. Little n is the number of turns per unit length. So we can use that expression to have B is going to be mu 0 times the turns per unit length times I. Let's do an example. If a solenoid has a length of 30 centimeters, diameter 2 centimeters, and 10,000 turns, 5 amps of current goes through it. What's the B field inside? And it's really just plug and chug on this. It's going to be mu 0 times 10,000 turns divided by 30 centimeters. And then we have the current, and the current is 5 amps. Okay, and so what we end up with is 0.2 Teslas.